Today we can discuss types of hybridization. The first one is sp3 hybridization. Sp3 hybridization is the intermixing of 1s orbital and 3p orbitals to form 4 orbitals of same shape and size, known as sp3 hybrid orbitals. An example is CH4. To understand hybridization in CH4, you have to write the ground state electronic configuration of carbon. What is the electronic configuration of carbon? 1s2, 2s2, 2p2. So the valence shell 2s2, 2p2. 2s that will be paired and 2p to unpaired electron. There are 3 orbitals in 2p. And at the time of the bonding, it will go to an excited state and hybridization also will take place. And here you can see 4 orbitals of same shape and energy are formed. Since all these are same energy, this electron will enter into the fourth one. Thus you will get 4 unpaired electron. And these 4 orbitals, the hybridized orbitals, are directed in space in order to avoid the repulsion between the electron pairs. So in this case, the shape is tetrahedral with a bond angle 109 degree, 28 minutes, as we discussed it in the case of VSCPR theory. Bond angle 109 degree, 28 minutes, hybridization sp3 in CH4, and here it is a scheme of hybridization. Of the structure, we can see the structure. Here the 4 hybrid orbitals are directed in space. 4 hybrid orbitals are directed in space to the corners of a regular tetrahedron with the bond angle 109 degree, 28 minutes. And each hybrid orbital that will overlap with the 1s orbital of hydrogen to form a sigma bond. You can see a sigma bond, sigma bond, sigma bond, sigma bond. 4 CH sigma bonds are formed by the overlapping of sp3 hybrid orbital of carbon and 1s orbital of hydrogen. Another example for sp3 hybridization is NH3. In NH3, the ground state electronic configuration of nitrogen 2s2, 2p3, 2s2, 2p3. Here the electrons are paired, and in 2p orbitals there are unpaired electrons in each orbital. In the excited state, it will undergo hybridization, excitation, and it will undergo hybridization. This 1s orbital and 3p orbitals are undergoing hybridization to form 4 orbitals of same shape and energy. They are sp3 hybrid orbitals. But one sp3 hybrid orbital contains a pair of electron, paired electron. Other 3 contains unpaired electron. Therefore, these 3 orbitals can overlap with the hydrogen atoms to form bonds. Here we are expecting a tetrahedral structure, but one is a lone pair that is not involved in bond formation. That is a lone pair. So in this case, we can expect a distorted tetrahedral structure. That means you will get a pyramidal structure, trigonal pyramidal structure with the bond angle 107 degree, because it has a lone pair of electron. Nitrogen has a lone pair of electron. So in the case of NH3, the hybridization is sp3 structure, pyramidal structure, bond angle 107 degree, and decrease in bond angle is due to the presence of a lone pair in the central atom, that is in nitrogen. Here you can see, here this orbital, this hybrid orbitals carrying a lone pair. There is no bond. But here, this hybrid orbital overlap with the hydrogen to form a bond. This sp3 hybrid orbital overlap with the 1s orbital of hydrogen to form a bond. This sp3 hybrid orbital overlap with 1s orbital of hydrogen to form a bond. So it has a pyramidal structure. Next one is H2O. H2O also has sp3 hybridization, and in the scheme of hybridization, ground state electronic configuration of oxygen 2s2, 2p4, 2s2, 2p4. Therefore, here a pair of electron, here also a pair of electron, and these two orbitals unpaired electrons are present. It can form two bonds. And in the excited state, it will undergo hybridization to form four orbitals of same energy and shape. Out of these four sp3 hybrid orbitals, two of them are carrying paired electrons, and the remaining two unpaired electrons. And here, since the hybridization is sp3, we can expect tetrahedral structure, but because of the presence of two lone pairs of electrons, a distorted tetrahedral structure will be obtained. And here the structure is bend shape because there are only two bonds. Therefore, bend shape or a V shape or angular shape with the bond angle 104 degree 30 minutes. What is the reason for such a reduction in bond angle? That is due to the strong repulsion between two lone pairs. Here you can see there are two lone pairs. So lone pair repulsion is greater than lone pair bond pair repulsion. So here you can see this hybrid orbital, sp3 hybrid orbital overlap with 1s orbital of hydrogen to form a sigma bond. sp3 hybrid orbital overlap with 1s orbital of hydrogen to form another sigma bond, only two bonds. Here paired electrons, so this sp3 hybrid orbital cannot overlap with any other orbital. This one also cannot overlap with any other orbital. So it is carrying paired electrons. So here it has a bend structure. Now sp hybridization. If one s orbital and one p orbitals are involved, in hybridization, we can call it as sp hybridization. And in sp hybridization, two atomic orbitals are undergoing hybridization, and you will get two sp hybrid orbitals. Two atomic orbitals are undergoing hybridization, and you will get two sp hybridized orbital. And these two orbitals will also directed in space to minimize the repulsion, that will be arranged linearly. So sp hybridized molecules have a linear shape, linear structure. And in sp hybridization, 1s, 1p. So 50% s character and 50% p character. An example is BeCl2, beryllium chloride. The ground state electronic configuration of beryllium 2s2, 1s2, 2s2, 2s2. There is no electron in 2p. In the excited state, this one s orbital and one p orbital will undergo hybridization to form new two orbitals of same energy and shape. They are known as sp hybrid orbitals. And here you can see two orbitals are remaining here in the unhybridized state, that is p orbitals. Two p orbitals are remaining here in the unhybridized state. Here the hybridization is sp, so the structure is linear with the bond angle 190 degree. Here you can see linear with the bond angle 190 degree. It is beryllium, it is an sp hybrid orbital. It is the second sp hybrid orbital. This sp hybrid orbital overlap with the p orbital of chlorine to form a sigma bond. This sp hybrid orbital overlap with the p orbital of chlorine to form a sigma bond. So BeCl, Cl, beryllium chloride. Now here, another example is C2H2, acetylene or ethine. It's another example for sp hybridization. Here, what is the ground state electronic configuration of carbon? 2s2, 2p2. And in the excitation, and at the time of excitation or bond formation, one electron from this 2s orbital will be promoted to 2p orbital and hybridization also will take place. sp hybrid orbitals with unpaired electrons here. But here there is a problem. In the unhybridized p orbital, there are unpaired electrons. So these p orbitals also can take part in bond formation. That is a problem here. These hybrid orbitals and also unhybridized p orbitals are present. Here you know there are two carbon atoms. It is the hybrid orbital of one carbon atom. It is the hybrid orbital of the other carbon atom. Two sp hybrid orbitals. And these sp hybridized orbitals of carbon will undergo overlapping along the axis, axial overlapping or direct overlapping to form a sigma bond. That is shown here. It is a sigma bond. And this sp hybrid orbital of this carbon atom overlap with 1s orbital of hydrogen to form another sigma bond. Here you can see. This sp hybridized orbital overlap with 1s orbital of hydrogen to form another sigma bond here. And now these two p orbitals are remaining with the unpaired electron. Therefore, that p orbital also will take part in chemical bond formation. Here, two p orbitals are represented. One is red and one is green. That is to identify them clearly. This green contain one unpaired electron, this red also contain one unpaired electron. Similarly, this green contain one unpaired electron, this red also contain one unpaired. These two orbitals, green, will overlap sideways to form a pi bond. Similarly, these red orbitals will overlap sideways to form another pi bond. So C triple bond C. One is sigma bond, the remaining two are pi bonds. Thus, the bond formation takes place, and here the bond angle will be 180 degree. Here also the bond angle is 180 degree, or this bond angle is 180 degree. I think it is enough for today, and in the next class we can see the remaining sp2 hybridization and sp3d and sp3d2 hybridizations. Okay.